Okay, everybody? Laptop shut and all the usual good stuff. Those of you at the back, do you mind coming up front? We have like 22 people in class, last count. So we can actually pack all 22 in the first row, or even conduct this class in my office. We're going to continue with, wait, is it 9? Yep, we're going to continue with our series on convolutional neural networks. This is going to be the last in the series. This would ideally have been completed last week, and we'd have had our guest lectures after we finished convolutional networks, but we cannot really predict when our guest lecturers will find time. So we tend to be a little flexible in our scheduling, which means that sometimes, things move around. So what you see on the course page may not be what I'm covering on any given day. Particularly, there happens to be a guest lecture which intervened, right? So here's what we saw with convolutional neural networks so far. This is what we're going to do. Today we're going to sort of go through a quick recap and spend some time on backpropagation through CNNs and look at some basic modifications and some success stories. So here's the story so far. We've seen that pattern classification tasks, such as does this picture contain a cat, can be done by scanning for the target pattern. So this gives you shift invariance. Now, scanning an input with a network and combining the outcomes is equivalent to scanning with individual neurons hierarchically. We've seen this too. So the first level neurons scan the input, higher level neurons scan the maps that have been produced by the first level neurons, and so on. And then a final decision unit or a decision network can actually handle can combine the decisions taken at individual locations. Now, for two-dimensional or higher dimensional structures where the scanning occurs in a two-dimensional pattern, we call this a convolutional neural network. On the other hand, when you had something like a speech signal or any time series where the scanning was only along time, this was a one-dimensional scan, we call this a time delay neural network or a 1D CNN. You've encountered both of these terms in your quiz. So here is the overall structure. I'll just do a quick recap. Here is your ConvNet. You had, it comprises convolutional and optional downsampling layers. Downsampling is optional. And when you have after a sequence of these convolutions and downsamplings, eventually you get some output which is passed through either a single neuron or a multi-layer perceptron. Yes?
If you use downsampling with convolution to extract greater than 1, does it take longer for the network to learn because it has to learn those parameters as well as opposed to with active learn?
These two are, the answer is not so simple that I can just, give it to you right now. The answer is we really don't know, right? It depends on the complexity of the problem, the network that you're modifying, and what learning algorithm you're using. So many different factors. But anyway, to get on, in each convolution layer, you have what happens is that you have two components. The first is the standard affine combination of outputs from the previous layer, which is obtained by a joint convolution over all of the maps in the previous layer. And then finally, this affine combination is operated on by an activation function, component by component, to produce the output. So we also saw what a convolution looks like, just for a quick recap. You have a filter of some kind, and you literally place the filter on top of the image, and at each position you perform a component-wise product and then sum the lot, and that's going to give you the output at one location. Scanning simply repeats this operation at every location. So we saw this too. And we saw what really happens is that you're not really you're not doing this for just one map. So in order to produce the output at any given location, you're going to have a collection of filters, one for every map from the previous layer. And so you'd be placing the filters over all of the maps in the previous layer, doing a component-wise product and summing the lot. And the actual scan is going to go something like that, right? So we saw this in the last class. A better representation is to just think of all of the maps in the previous layer as forming a cuboidal structure, so you can stack them up. And your neuron, which we said we would also call a filter, is also a cuboidal structure by itself with many little planes. And the process of, so this would be a neuron. These are all of the stacked arrangements of maps from the previous layer. And the process of computing the output at any given location in the next layer, that is the affine output at any given location in the next layer, is performed like so. You would place your filter at the corresponding location with one corner of the corresponding location on the maps, on the stack of maps from the previous layer. And then you perform a component-wise product of your filter values and the values on the maps and add the lot up. So this was the operation that we saw. Now, since this is really just a neuron, the neuron actually always comes with a bias. So there's always this bias term, which is specific to the neuron, not to the location, right? And so scanning, observe that this B of S is going to stay the same, right? And so scanning is simply moving that filter all the way from the top to the bottom, and at each location repeating the operation that we just discussed. So in vector notation, we saw that the entire operation can be written using this little pseudocode. You would be going through the layers in your network, and within each layer, you'd pick each filter, each neuron, and that neuron actually corresponds to a spatial span x and y. So you'd slice out the corresponding region of your input maps, the stacked input maps, which is now going to give you a cuboid, which is a 3D tensor, and then compute a component, an inner product between your filter and the sliced out tensor, which is to say it's a component-wise product and a multiply. And then you'd also, this is kind of not showing the addition of the bias. If you did this right, you'd also have the bias term added. So my pseudocode has a few holes here and there, and then you put that through the activation and you get a softmax. And then you'd go through the layers, and eventually when you got to the end of the layers, you'd combine the outputs using a softmax or what have you. Now, convolution can shrink a map if the stride is greater than 1. We saw this too. So if I skip by more than one position at a time, the output is going to be smaller than the input. And so taking a stride with 1 gives you an output which is the same as the size of the input, provided you account for the borders. If the stride is greater than 1, then the size of the output maps is going to shrink. So if you were to look at the pseudocode for this pseudocode is going to look exactly like what we did for the standard convolution, except that when I'm striding over scanning the input, I'm going to stride and jump in steps of length stride, this variable stride. So if your stride is 2, you'd scan at some position, then take 2 steps forward, scan at the next position, and so on, and then compute the input at that position, and so on, right? Now, the other method for shrinking the maps we saw was through downsampling layers. Now, this is where we actually begin to get into today's material. All of that was a recap. Now, these downsampling layers, they typically sort of come immediately after each convolution layer, but you can actually have multiple convolution layers before you get a downsampling. So these are optional and don't necessarily have to alternate. For example, here, after the first 2 convolutions, you have downsamples, but then the third downsample actually follows 2 convolutions. So here's what we had different kinds of downsampling layers. We saw max pooling where you would actually be looking at a small region of the input and picking just the largest value. So here, for example, you might be looking at this region where the output of the layer might be, say, 3, 1, 4, 6. You just pick the largest value, which is 6, and then you just scan them using exactly the same operation as before, right? So the pseudocode for max pooling would look something like this. Now, observe something interesting. The way I have written it, at each location, again, max pooling is going to typically stride by more than 1. So we saw that too. But observe that what we are doing at each location, we are looking at a region of the output of the convolution layer. The output of the convolution layer is the output after the activations have been computed, the affine combinations have been computed, and the activation has been applied. Okay, so we are looking at that output, and we are finding the index of the largest value. So this, note the sequence of operations. This is going to be important when we actually go to perform our backpropagation. And then the actual value that you store is the location of this output at this position. So you're not just picking the largest value, you decompose this into a two-step process, where in the first step you find the location of the largest value, and then in the next step you read the value at that location, right? So also this is performed independently for every map. So remember that when you actually perform the computation, you're going to get several maps which we stack up. But the actual max pooling operation that we perform, this is going to be, when we did the convolutions were combining all of the maps. When you perform the pooling is performed individually on each of these maps. Instead of max pooling, we could have mean pooling. We saw this too. So in the mean pooling variant, instead of picking just the largest value of this collection, you're going to average this collection, and so you find the average value and store the average value, right? And so scanning is now going to just scan over the input, and within each block you pick the average value and store it. So this was the pseudocode for mean pooling. Now because you're mean pooling, now there's no notion of a max. You're not storing the location of the max. All you're doing is computing the mean of the little block over which you're performing the pooling, and just storing that value. So putting everything together for a typical image classification task, if I were assuming max pooling, here's what we saw. You'd have some input, which is typically an RGB image. So the RGB is going to give you three layers of input, which you would stack together, and so now the input itself looks like a cube, right? You would have each layer of your convolutional neural network is going to consist of several filters, each of which by itself is a cuboid. And so all of these filters would scan your input and produce a collection of planes, over which you perform some pooling operation, get the reduced planes. Then over these you would operate with another collection of filters and get some outputs which you could pull together. You repeat the process till you're done with the convolution and pooling, and then finally you sort of take all of your outputs and then stretch them out into a single vector, an operation that we call flattening. And then the flattened output is passed through either just a softmax or an MLP. This was the complete operation, right? So the parameters to be learned are the weights of this guy and of this final MLP, and each of these filters, the filters, collection of filters for every single layer. Now this is where we stopped. Now what is this business of learning the CNN? Learning the CNN is just like a regular MLP, because as we saw, the convolutional neural network is just a traditional multi-layer perceptron with a minor variation, which is that the parameters are shared and you're scanning the input with this MLP. But you can think of the whole thing as just one giant MLP with shared parameters. And once you think of it that way, then backpropagation and training becomes literally a very trivial process. But then let's go through the mechanics of it. How actually would you implement such a thing, and what do the equations look like? So first, you're going to define, you would assume that you have training examples where you have the images and their class labels. You define a divergence between the desired output and the true output of the network in response to any input. And then the network parameters are trained through variance of gradient descent, the same techniques that you've used in homework 1, for instance. And the key portion is that the gradients are computed through backpropagation. So here's what you'd have. You have the entire network, and you compute some output in response to some training input. Now you have a desired output for that training input. So you might say that this is an image of a house. The network has some output. And then you can compute a divergence between the network output and the desired output, typically a cross entropy loss or a Kullback-Leibler, which is a Kullback-Leibler divergence. And so now you have a divergence which is defined between the output of the network and the actual output that you want it to produce. And subsequently, you're going to compute derivatives. So here's what the loss looks like. You're given a collection of training samples. For each training sample, you can compute a divergence. The overall loss is the average divergence over the entire training set. And what we want to do is to learn all of the parameters of the network, which are all the weights and biases, to minimize this loss. So this procedure is the same as before. You would initialize all of them, and for every filter in every layer, for every filter parameter of every layer, you're just going to use the standard gradient descent rule. Now, the gradient descent rule, of course, requires the computation of this derivative, which is the derivative of the loss with respect to each of the parameters. And the loss we know is the average divergence over all of the training samples. So the derivative is going to be the average of the derivatives of the divergences for each of the training samples with respect to the parameters. So this is what we really want to compute, right? Now, this is where backpropagation kicks in. Now we know how to perform backpropagation through a standard multi-layer perceptron. So for these flat layers, there's nothing new to be learned. We know exactly how these things are performed. It's just a standard MLP. If I have defined a divergence over here, I can compute the derivative of the divergence. I can propagate it backwards all the way till here. Now, as I go back through the network, I'm computing two kinds of derivatives. First, I'm computing derivatives with respect to the parameters themselves, which are the weights and the biases. But then I'm also always computing derivatives with respect to the output of the previous layer, right? So which means that by the time you come to this position, you actually have the derivatives with respect to the outputs of the final convolution layer. That's what you're going to be you're going to continue to propagate backwards. Now, those derivatives for the final convolution layer will look flattened out, but then you can fold them back into the same shape as the final convolution layer itself. So you have the derivatives with respect to each of these positions. Now, let's see how those things move backward. Because when we propagate those derivatives further back, you're going to need some adjustments. Now, for some reason, my TA is missing today. Okay. Now, when you actually begin computing these derivatives going back, you have to take care of a few things, right? So by the way, Soham, do you have Vedant's number? Can you ping them and tell them that somebody should be here? Yeah. So let's see how this actually works out, right? Now, observe what happens here. When you're going forward, now what does the derivative compute? The derivative says, how much does changing this little value changed my final function? So now we need two kinds of derivatives when we're backpropagating. One, of course, the derivatives with respect to the weights, but more importantly, you need the derivatives with respect to the outputs, the y's, for each layer, because those are what are being propagated backwards, right? And now here's what happens. If I'm trying to compute the affine combination z for any layer, a single y in the L-1th layer is going to affect a whole lot of z's in the next layer. So to see how this happens, take a look at what happens with this one blue box, right? So if as you scan, observe that blue keeps falling within the orange patch for every location. In other words, that blue box has affected the output for every one of these locations in Z, right? So that in turn means that when I'm computing derivatives, I have to capture derivatives over here, and derivatives with respect to every one of these Z's are going to be required, and they're all going to contribute when I compute the derivative of the divergence with respect to this one little blue guy, right? Everything has to actually go backwards. So basically, now let's go forward. So now once I've computed the activation in any particular layer, computed the affine combination in any particular layer, I'm going to apply the activation and get the output for that layer. And the activation, of course, is applied position by position. So that's an easy bit, right? And so here is what we have. This green patch is the output of the L-1th layer. The pink one in the middle is the affine combination of that you obtain for the nth layer, and then the gray at the extreme end is the activation applied to the nth layer, right? Now, when I'm going backwards, then here's what I need to do. I'm going to assume that as I backpropagated, I already have the derivative with respect to all of these y's in the nth layer. And I have to use these to go backward to compute the derivatives with respect to z, and then take a step back and compute the derivatives with respect to the y's in the previous layer. And somewhere between here and here, I also need to compute the derivatives with respect to the weights. I'm going to assume that the bias is also just a weight, so we won't treat the bias specially. Okay. Now, this portion is easy, right? Because if I already have the derivative with respect to all of these y's, now each y is computed from a single z. So if I want the derivative with respect to a given z, now I'm indexing z with four indices over here. L is the layer, M is the map, x and y represent the position, right? Now, the derivative of the divergence with respect to any z is simply going to be the derivative of the divergence with respect to the corresponding y times the derivative of the activation at that z. This is just, again, straightforward what we've done in the past, nothing new, right? So I have the derivative of the divergence with respect to z is derivative of divergence with respect to y times the derivative of y with respect to z, which is simply the derivative of the activation function. This bit is where we have to begin taking a close look, right? Again, here we know that each y in this map affects several z positions, right? So all of them will go back and contribute to the derivative with respect to that y. In fact, so let's say I have this, consider this particular y. I'm choosing a different y simply because it's closer to the corner and it's easier for me to illustrate things. Also, this won't generalize, and if I just show you the figure, the y in the center, it may convey the wrong impression because that y actually explicitly affects every z in the next layer. This one does not, right? So now this guy affects several of these z's. In fact, it affects all of these 4 z's. You can see why, right? And why does it affect those 4 z's? How do you know when a y affects a particular z? So let's say I have my y map, right? And consider, say, this y, okay? This is my z map. Now, if my filter is positioned over here, starting at this corner, this y falls within the region for the filter, right? So placing the filter here is going to compute the z over here. So this y has influenced the z. If I place the filter here, like so, the y still falls within the filter, right? And so this y now ends up influencing this z, because this placing the filter here is computing the z value for this term, right? Now, if I slide the z value, the filter one step forward and put the filter here, the y is no longer falling within the filter region. So this is not being affected, right? So also when I slide this downwards, if my filter is positioned here, the y falls within the filter, so the y clearly influences this z, right? So what is the principle that you get? What is the last z that the y will influence when indexed in this manner? The last z that the y will influence is when this y happens to be the top left corner of your filter, right? After that, the filter is simply going to slide off from the y. And so this y is going to influence everything from that position here upwards for the area of the filter. That makes sense to everybody, right? So each y is actually going to influence several z terms. And in fact, it's not going to influence the z terms in just one map. It's going to influence that set of z terms for every one of the maps, because convolution is basically using this y to compute each of the output maps, right? So how does it influence it? Now let's say I have, so let's say this is the, what is the index I'm using it? This is the mth map, right, for y. And this is, say, the nth map for z. So the weights that will be that are going to be used are specific to the mn pair, right? Now let's look at how a y over here, which let me call this xy, influences a z over here. Let me call this, say, x prime y prime, right? Now this y will influence this z if the filter is positioned at this location, correct? With the top left corner at that location. So if the filter is positioned with the top left corner at that location, then what is the index of the weight with which this is multiplied? That is going to be the position of the y with respect to the location of the filter, right? So you're positioning the filter at some location, and you're counting the index of the y with respect to that, and that is the weight with which the y is being multiplied to influence the z, right? And so that index is going to be, this guy is, say, xy. Let's say this is x prime y prime, right? So this index is going to be just, what will it be? Make sense to you guys? I seem to have lost you. So what would the index be? Yes? It's just going to be x minus x prime y minus y prime, right? So basically, again, going back here, I have my, if I'm looking at, say, I'll try to clean up the figure. If I'm, say, looking at this y map, and I chose some y xy, I'm not showing the map index, right? And I want to figure out how this y influences the z at this location, right? Because I'm going to have a corresponding z, and I want to see how this y influences the z at this location. To do so, I must place the filter with this z as the top left corner, correct? So this index is x prime y prime. This index is xy. So which is the index of the weight with which this xy is being multiplied when you compute the z value over here? That is going to be, in this case, 1, 1, right? That's the location 1, 1. Or more generally, it's going to be x prime, x minus x prime, y minus y prime. Make sense to everybody, right? So in other words, this each y influences several z's, and each z in any map ln x prime y prime is going to be, this is the layer, so the layer is going to be the same. The L minus 1th layer influences the z maps in the Lth layer, so you don't need to index the L, but then, I mean, the weights are specific to the Lth layer, right? The weights are connect the y map in the mth layer to the z map in the nth layer, so you have the index mn, and the positional index is going to be x minus x prime and y minus y prime, right? That is the weight value with which any a given y influences any given z. Now this is going to be key. You just have to, it's not very complicated, but it's something that you have to remember, okay? So now, for every Lth layer, right, y influences several z's through this weight, we know. And so, for example, this guy influences all of those guys. And it's going to do this for every one of the maps, correct? So in other words, if I want to compute the derivative, so this y influences all of these z's. If I want to compute the derivative of the divergence with respect to the y. How do I do it? The way I would do it is I'm going to be summing over all z's such that they are influenced by y, right? This is the derivative of the divergence with respect to z times the derivative of z with respect to y. I mean specific components. This is how we'd actually compute the derivative, remember? So this, of course, is going to be, so what is the derivative of the divergence with respect to, say, some y xy, m xy? So which are all the z's that the y will influence? It's going to influence every map, correct? So you're going to be summing over all of the maps in the nth layer, n equals 1 to n, let me call this, right? If you have n maps in the nth layer, you're going to be summing over all of the maps in the nth layer. So this is derivative of divergence with respect to z, and then I'm not showing the index, but I'm showing you the map index, right? And then you're going to be summing over the entire region of z, because every single z is potentially influenced by the y, right? So it's going to be summation over all xy in the z. Let me call this x prime y prime, right? And then the derivative of the z and with x prime y prime with respect to derivative of y xy. This we know, right? Again, I'm not doing anything complicated. But what is this term here? What is this term here? We saw how every y influences a z, right? And what did we multiply the y by to compute the z? So what did we multiply zxy, the y value at this location xy? Okay, and you're reusing the symbol y, but that's kind of bad. But what would be computed? What would we be multiplying the y value at the location xy to compute its contribution to the z value at x prime y prime? Yeah, and what is the weight? It's going to be x minus x prime. I can actually erase this, right? And so this is going to be, this is simply w connecting the mth layer to the nth layer, and the index is x minus x prime, y minus y prime. That's this term, right? So once I write this, the rest is easy. I can just write down the formula. The derivative of the y with respect to divergence with respect to any given y, here I've actually shown you the layer indices, is going to be summing over all of the maps, all of the z maps in the next layer, right, over all of the positions in each z map, and this is going to be the derivative of the divergence with respect to the z times the derivative of the z with respect to the corresponding y, right? You see exactly how this little computation came about. It's not, it's trivial, okay? If you actually work your way through, it's trivial. Make sense to you? Yeah, okay. Now, what about the derivative with respect to the weights? That's what we're really interested in. I mean, that is also something we're interested in. Now, this becomes a little more challenging, right? Observe that this weight, any given weight, so any given weight, w, m, and say, let me give this, say, uv, right? uv are indices. Now, any given weight is specific to a particular y map and a particular z map, right? So it's literally connecting. So I have several y maps, but I don't care. I have several z maps. This is y, this is z, right? I have several z maps, but a particular weight is, because it's indexed by the maps on either side, a particular weight is specific to a pair of y and z maps, correct? So that's all we really have to consider. Now, what are all the values of z that the weight with index uv influences? So if I put the filter here, right, and if this is uv on the filter, right, then it's going to be influencing this guy, this z, but it's going to be influencing this z through this y. That makes sense? Right? So you have this connection. The weight is going to influence this z through this y. Now if I place shift one step forward and place the filter here, now that same weight is at this location, correct? And it's going to be using this value of y, and it's going to be creating this value of z. So you have this, the z influencing, the weight influencing a new location of z through a new location, a new position on y. That makes sense, right? And similarly, so now if I finally position the filter here, this is the weight value, right? It's going to be influencing the z over here through the y over here. That is the connection that you'd actually be seeing. So what we find is that each weight influences several z terms for every n, but then it only affects the z's in one map. But here is the thing, right? If I want to compute the derivative with respect to the weight influences all of these z's, right? And so I have to add the contributions to the derivative of the weight from all of these z's. And specifically, how does the derivative with respect to, say, the weight of some uv, what is this derivative of this divergence with respect to uv, right? Weight uv. So this is going to be, obviously the weight affects several z's, so it's going to be affecting the entire z map, as we saw, right? So you have the derivative of the divergence with respect to zxy, and then times the derivative of zxy with respect to the weight. But what is this term here? This term, observe that zxy is going to be influenced as w uv times y of which position is it? What is the corresponding y position that multiplies the w to compute the z? X plus u, y plus v, right? So this is, if you look at this guy is being influenced by this term. So 0, 0 is being influenced by uv, correct? 1, 0 is being influenced by u plus 1 v. If I go here, if I place the filter here like so, then you're going to find that 0, 1 is being influenced by u v plus 1, correct? And so this is going to be x plus u y plus v. Make sense? And so here's what we'd find. The derivative, I'm using a different index. I'm calling this, instead of uv, I'm calling this xy, but you get the same notion, right? You're summing over all of the z's, the derivative of the divergence with respect to the z times y of this x prime plus x, y prime plus y. Make sense, right? Where the arithmetic came from. So you're summing over all zy pairs that are multiplicatively related by the weight. So now we can actually just write this into a little bit of pseudocode. Now the arithmetic seems very painful, right? When I actually sort of work this out, you have to figure out what the indices are, use your brains, do the maps, try to find out what relates to what. When you write code, it becomes much easier. It's kind of it's a bit of a shame that the code is so much simpler than the math. Why is that? It's still for the derivatives, right? here's what I can actually take advantage of. I have a fear that as I write, this board will slide upwards. Stop. Okay, so you have a few seconds to figure out what I'm saying. All right. Now observe this. In the process of any computation, suppose I have some, y equals w times, or z equals w times y, right? And then I have some function of z that I've computed. Okay? Then the derivative of f divided by derivative with respect to w, just obtained from this equation, is simply going to be, it may have other terms, but the contribution of this particular relation is simply going to be the derivative of f with respect to z times what? What would it be? Just y, right? I just have to write that. So also the derivative of f with respect to y plus equals df over dz times w, right? So look at that while before it slides up. I just do that. Now here's your forward equation for CNNs. When I wrote down the forward equations for CNNs, you went through the layers, you went through the filters, each filter scanned the input, correct? And that each input, what did you do? You positioned the filter at some location, and then you computed a pairwise product of the filter position and the y and added them up, right? So these are the indices. If you position the filter at location xy, then filter x prime y prime is going to be multiplying y of x plus x prime. The minus 1 is to account for 0 for the shifted index. Here the indexing starts from 1, right? Now let's apply this. These computations are independent within each loop, and you're going backwards. So now all I'm going to do is to take this little piece of code and apply this logic and just say, so z is a product of w and y. Taking a step back, the derivative with respect to z, y, is the derivative with respect to z times w, and the derivative with respect to w is the derivative with respect to z times y. All I did was just take this piece of code, and change one line, right? The forward code changed by one line. That's all that happened. Nothing more complex, right? So although the math looked very tedious, when you write down the code, I took my forward code, I changed one line, and the whole thing will just work, right? So long as my forward code is right, this thing is going to be fine. Of course, the one thing that you're doing is now you're going to actually be going backwards from the, you won't be computing this forward. You want to make sure that every derivative that you're using has already been computed, right? So, and this whole thing can be cast in, there are multiple ways of casting this as tensors. I won't actually go through this. Now, if I were using strides, right? Now, if I were to write down the arithmetic and worry about the strides, it becomes a lot more painful to find how the indices map up and so on. But then when you look at the code, it becomes trivial. So what did I do? All I did was to make the scans go forward in strides. So I just took the forward code that had strides and replaced the affine line in the forward code with this version, and everything works. So I don't even have to worry about the striding and all the rest of it. From the code perspective, this actually becomes very simple and very trivial. Right? Make sense to everyone? Right. But then let's actually go and look at it from a slightly different perspective, because this is what you're likely to encounter if you actually saw some publicly available code, and because it makes sense. Now this of course makes a lot of sense. It's trivial. Everybody can grasp it. There's nothing magic. I just used one little piece of arithmetic and everything fell into place, right? But then there's a different way of looking at it. So let's see how this y actually affects the A given map in the next layer. Okay, so look at this xy. Now this xy, this is my filter. I've color coded the filter and showed you the indices. just to make things very clear, right? Now, if I want to compute this z over here, which filter value will this xy be multiplying when it contributes to that z? Pardon me? Will it be applying? No, because remember, I have this, right? I have my, in this particular case, I want to find out how this xy influences this z. For this to happen, I must place the filter up here, correct? Which filter index? This filter index is what influences the corresponding z, correct? So if you look at that, that guy, the bottom right filter index influences this y, right? When I'm trying to compute this xy, okay? What about this one? This xy clearly also contributes to the second z. Which filter index will be used in computing it? 1, 2, right? The color code is being shown, right? And then this one will also influence this z. Which one? Which index? 0, 2, right? And then it's not going to influence anything further down, correct? Now this xy influences this z. Which weight index would that be? 2, 1, right? And then that one is going to be, the next one is 1, 1. The next one is 0, 1. This is 0, 2. Okay, it's 2, 0. It's 1, 0. And then 0, 0. Okay. Observe something very interesting. Each xy influences every z, and the influence pattern is the exact mirror image of the weights. Top to bottom, bottom to left to right. Make sense to everybody, right? So when I want to compute the derivative of the divergence with respect to, say, this xy, then the contribution of this xy is going to be the derivative of the divergence with respect to this xy times w0, 0, right? The contribution of this guy is going to be the derivative of the divergence with respect to this term times w1, 0. So I'm computing the derivative of the divergence with respect to this xy, but I'm looking at what comes through this position, right? So you see how the whole thing is working out, right? So if I want to compute the derivative of the divergence with respect to all of the z's, to compute the derivative of the divergence with respect to the y at this location, I have to mirror image the filter and then place it with the bottom right corner at this xy. Do a component-wise multiplication and sum the lot. Make sense? Right? And so for every single location, so this is what happens, right? You're going to be doing this over all of the maps. It's not just one map, because this xy influences all of the maps, correct? So what you would be doing is you'd be summing over all of the maps, but within each map what you're really doing is positioning the mirror imaged filter with its bottom right corner at the location for which you want to compute the derivative, doing a component wise multiply, and then summing the lot. So here's what I would be doing if I want to compute the derivative with respect to y at this location. First I'm going to start with my filter and I'm going to mirror image it. Then I put the mirror image with the bottom right corner at this location, do a component wise multiply and add the lot, right? And I can keep going forward, and this is how I would actually compute my derivatives, right? Make sense? What is this operation? This is just a convolution. What am I convolving with? Still the filter, but now the filter has been flipped top to bottom, left to right, right? Make sense to everybody? Except you're not looking at just one map. You'll be looking at simultaneously at all of the Z maps in the next layer. So for all of the Z maps, you're going to have, the filter is going to have one plane for each map, correct? So each of these planes is going to be mirror imaged, left to right, top to bottom. And then you'll be placing these guys like so, and then doing the component-wise multiply and summing the lot to compute the derivative with respect to a given y, right? So to compute the derivative with respect to this y, here's how you'd place the filters and perform the computation. And then you can see how the computation actually progresses on the slide. Right. Make complete sense to everybody, right? Pictorially. When you begin writing the math, it's often very tedious. But then when you actually visualize what's happening, it becomes trivial, it becomes very simple, right? Now observe something very interesting, right? To compute the derivative over on the top left corner, the filter began its life outside the z-plane, correct? Because only the bottom left corner of the filter was on the z-plane. So also when you computed the derivative with respect to the bottom right position, computed the derivative with respect to the bottom right in the y-plane, the z is hanging off the edge, right? Why is this happening? Because when you compute, remember when we convolved forward, the actual number of outputs you could compute was smaller than the number of inputs because the filter couldn't really fall off the edge, right? But when you go backward, you have to allow it to do that. So if you actually want to implement this, how would you implement it? Yes, zero pad, right? So this is just a convolution by the inverted filter, as we saw, but after zero padding it with L minus 1 zeros on every side, right? And so once you know this, you can actually use your forward code to compute your derivative going backward, can you not? All you would do is mirror image your filter, compute your derivatives. Make sense to everybody? Yes.
What happens if you have padding? How do you go backwards if you have padding? Do you just ignore the padding?
Then in that case, you don't need to pad, right? Because you've already got the full size Z. But this is exactly what happens, right? So you'd have to make sure that you get the sizes just right. Yeah.
What about with strides in between?
What do you think will happen?
Say like 2 or something. I am assuming we have to.
It's going to be exactly the same convolution with strides, right? Because that's exactly what's happening. The arithmetic remains the same. Okay, so this is, I'll let you figure this out, work out the arithmetic and post it on Piazza now that you volunteered, or rather I volunteered you. So this figure, you can do this with slides for me and write the equation, right? Thank you, with strides. So easy. Now, so we see how you can compute the derivative with respect to the y's. Turns out when you're computing the derivatives with respect to the weights, this simple convolution interpretation that I just showed you needs a little bit of tweaking. Again, I'll leave that to you to figure out how it's done, because I'll move on, right? So now pooling is typically performed with strides greater than 1 and results in a shrinking of the maps. So this is what we did, remember when we were pooling, right? And at each location, what did we do? We did a two-step process. First, we found the position of the input where the value was maximum, and then you copied the value of at that position, right? Now what does a derivative mean? Go back to our definition of a derivative. A derivative really says if I change this parameter a tiny bit, how much does the output change, right? So if this is the value that I've chosen to copy over here, then would modifying any of these three guys change the output? No, right? Because they don't influence the output at all. Only the one that is largest influences the output. So what would the derivative with respect to these three guys be? 0. So clearly, on the other hand, what is the derivative with respect to this one? It's simply going to be the derivative with respect to the z over here, right? You just copy it straight down. And so when you compute the derivative with respect to any y, the derivative with respect to that y is going to be the derivative with respect to the corresponding pooled map if that location has been picked as a maximum and 0 otherwise, right? In other words, basically what you're doing is copying the derivative with respect to the map into the location of the maximum, and the rest of them are being left unchanged. So yes.
If we have two maxima, do we have to store both indices?
So you would be picking one, right? Yeah, but yeah, I think you'd actually have to split the derivative to both. Okay. Or assign it to any one. Whatever operation you perform going forward is going to be reversed. You stored an index, that's the one that's going to influence it, right? So again, that's because you have this issue that at the specific hinge that you get a subgradient rather than a gradient. A max is really non-differentiable in those situations, right? So here's how the pseudocode looks. All I'm doing is in the forward, I'm storing the PIDX, and then I'm computing the value of the y at that position. And the backward, I'm just updating the derivative with respect at that location by the derivative for the corresponding downsampled map. Okay. Now I'm using a plus equal to simply because after strides, a specific location in a y map may occur in multiple windows as you're going frames as you go forward, right? So it's not, so a particular y location may contribute to multiple outputs in the downsampled map. So this shows a plus equal to. What about mean pooling? Now mean pooling is somewhat different. Mean pooling, you're actually taking the average. So this value is the average of all of these four, which means it's the sum of these four terms here divided by the size of the window itself, the size of the filter itself, right? So going backward, if I have some derivative over here, what would the derivatives with respect to these four terms be? It's just going to be 1/4 of the derivative there because it's going to be spread out, distributed over all four, right? So the derivative for all of these locations is simply going to be 1 over k squared of the derivative with respect to the corresponding output. So if you actually wrote down the pseudocode, this is the operation going forward, right? The mean pool at any layer is the mean of the little region that you're considering. And going backward, the derivative is simply going to be, this should have been a deal. That's a mistake, right? It's going to be the derivative with respect to u divided by the size of the window. That's just going to be added right back in, okay? So we've seen how the derivative of divergences with respect to every intermediate output and every free parameter can be computed. And now this can be embedded into a gradient descent framework to learn the network. Questions? Right. So we'll begin meddling with a few things. First, we assume that when you're scanning, you're either retaining the size or you're shrinking things, right? So can you actually increase the size after scanning? And what does this mean to increase the size after scanning? Now, what we did is if you had more neurons in any layer than in the previous layer, the output map, the size of the output map didn't change. What changed was the number of output maps, right? So although you could have more outputs after any particular layer, the size of the map itself either remained the same or shrank. Can we even increase the size of the map? How would we do this? So to give you an idea, we've seen a figure like this before, right? Where have we seen this? So many times. Your quizzes, right? And your homework, okay. And the notes on Piazza, okay. Now, I'm going to sort of observe that I've drawn all the lines over here. I'm just going to choose the simplified version. So this arrow really means this arrow contains 6 weights. You have 2 input neurons going to 3 output neurons. So this was the scanning MLP that we performed, right? This MLP, in this case, is scanning, and it's got a stride of how much? 3, 4, 5, 6, 7, 8, 9, 18. Right? It's a distributed parameter network, but it actually has a stride of 18. It's scanning this location, then jumping forward by 18, then scanning this location, then jumping forward by 18, then scanning this location. I think it's 18. Am I right? Yeah. So you see how this is happening, right? This is scanning the input with a stride of 18. Although the individual neurons have much smaller strides. So this is, I want to, and we actually worked out these relationships in your homework, I'm pretty sure. So you have this thing, you have this, you've understood how this works. Now, observe what happens. As you go upwards, each bar represents one layer, right? The number of circles in the bar represents the number of channels, basically. So what has happening is when you scan, the number of bars either stays the same or keeps going down. So it has a tree structure. That's because when I'm scanning, each of these blocks is looking at a certain number of inputs, and then it's striding by an integer number of steps. So you can either have the same size or you can reduce. If my stride is greater than 1, it's going to reduce. So in this case, for example, here the stride is 2, correct? For the lowest layer. So after every 2, it's jumping. So the first set of bars is going to be half as many as the lowest set of bars. Over here, the stride is 3. The second set of bars is going to be 1/3 as many as this first. The third set of bars is going to be 1/3 as many as the second set of bars, and so on, right? But then, what if I have a fractional stride? What do I mean by having a fractional stride? If I have a fractional stride, this means that in some layer, as I'm going upwards, I'm going to have more neurons, or more bars than in the previous layer, like in this case. So here, for instance, I have 3 bars in this layer, right? But the next one actually has 6 bars. So how does this work? Now, once I begin doing this, the basic structure of symmetry that I have assumed so far can no longer be retained, right? Because this is the actual scan happening. What is happening is now I'm scanning a much wider region of the input, and this is the tree that's actually scanning the input, correct? And once I look at it this way, you realize that these 3 neurons need not all be the same. I'm just scanning up, right? These 3 bars. So in fact, what we have is these 2 guys are the same, but this one is different. When you actually look at it like so, right? So a different way to see what happens when you actually have more neurons, a greater bar density at any layer than in the previous layer, is to say that that in the area with the greater bar density, you're going to have multiple types of neurons, right? So earlier, every bar was identical to every other bar. Now every bar is not identical to every other bar, right? You're going to have some patterns. So how would the actual computation go? If you're going left to right over here, for instance, so you would have computed this one at some point. Then you take the next step. This one is going to contribute to all 3. Since this has already been partially contributed, this is going to add, it's going to, everything, the information flowing upwards is always going to contribute additively. So this would contribute to this, this, and this. Then you take the next step. This is going to contribute to this, this, and this. Observe that this gets a contribution from only one of the lower bars. These guys get contributions from multiple of the lower bars, right? And so you continue your computation left to right. So here are the connection rules. In shrinking layers like these, the patterns of incoming weights is identical for every bar. But then when you have expansion, obviously you have asymmetry. You have asymmetry on the row above, but on the current row, the pattern of outgoing weights is identical for every bar. So for these guys, when you have an expanding layer, this pattern of outgoing weights is the same as this pattern of outgoing weights. Make sense, right? And so the point is, when you think of this and you think of the whole thing as a scanning MLP, what you will find is that in terms of bars, this guy, you have 1 going to 3 upwards, right? So if I think of the weight matrix, when you're going up in a standard tree, then the number of outputs is smaller than the number of inputs, so output bars. So the weight matrix is going to be broader than its wide. When I'm going the other way, when I'm doing this, the weight matrix is going to be wider than its broad, right? So it looks like a transpose of a regular weights matrix. So for that reason, they actually like to call this a transposed convolution. Although strictly speaking, that's not that's not a very great terminology. But you see how the computation is being performed. But let's go through this mechanically, right? So if I'm doing this, that's for 1D, right? For 1D, I just set up the layers, and then I can just keep scanning left to right with the lower layers and keep filling things in. So if I had this in 2D, right? So let's say I want to increment the size of the map. Then at some layer, I would have a map of this kind. I have some filters. The way you increment the map is going to have a stride greater than 1. Now you can have, so you can think of this as it's a fractional stride in a very bizarre kind of way, right? See what happens over here. So for the first output, now this one is actually going to be, these guys are going to be contributing to all of these positions. Then the next one, you're going to be striding forward by some step, by some integer, and they're going to be contributing to all of the positions shown, right? And this is basically exactly the same, it's strictly analogous to what we saw in the 1D case. Here's how the computation will be performed. So for the expanding convolution, you can see I have the pseudocode over here. You're actually going to be jumping forward when you're filling in the affine combinations and performing the computations. Now, given this equation, do you know how to compute the derivatives? It's trivial, right? You can just use the same code, split this up, and compute the derivatives. Again, we've seen the trick for how to compute derivatives easily, so you don't have to spend a lot of time working through the math. You just work with the code. It's much easier. Okay? So we leave the rather trivial issue of how to modify this code to compute the derivatives to you. Okay? Now, so this stride is the scaling factor. The whole operation is again often called a transposed convolution, because if you think of this as an MLP, now the shape of the weights matrix looks transposed with respect to the shape of a traditional weights matrix. We've had many questions. What about scaling? You're scanning for patterns. What happens if the patterns scales up? Yes?
Professor, in the last slide, I mean, it's just that now we have just a stride, right? Like
Yeah.
if we increase the number of weights matrices that we had, the parameters we increased, and we just need a stride of 2. That the weight
Increasing the number of weights matrices is going to increase the number of output channels, right?
Yes.
Increasing the stride is going to increase the size of the map.
Yeah, so it's a normal convolution only with a more number of weight matrices. How is it fractional and how is it helping us?
So if you think about the Z effectively, right? Now, if my stride while scanning forward is 1, the output is the same size as 1 as the input. If the stride is 2, the output is half the size of the input. What do you call it when the output is twice the size of the input? The effective stride is like I'm stepping forward half a pixel at a time, right? Make sense? The computation is maybe not exactly that simple, but implicitly that's what's happening. Yes, Michael?
After you did the first convolution, the image seems to suggest that you get 9 outputs.
Yes.
So how do you get more than 1 output from a convolution?
I've just multiplied this value by this weight, and there's no summing. I just put it right there, right? Or there's the depth issue involved, of course, but right. So you'd be summing over these guys, but not over the filter. Yes.
This might be going back to the 1D illustration. On the very right, there was a bar that wasn't yet.
because the computation continues forward, that's all. Right? I'm showing you a central slice. Okay, so now I'm going to run a little over, guys, because I want to finish this today, right? And I have 11 minutes left. Now, this business of invariance, how do I account for patterns that are rotated, for instance? I'm looking for flowers, but if I get the same flower with a little bit of a rotation, will I still detect it using the standard CNN? You won't, right? Because you've learned about face-on flowers. What if the size of the flower is scaled up by a factor of 1.2? Will you detect it? You really won't, because you've learned to detect patterns of a specific size. So, given this, how can we modify this model to be able to account for these variations? Now, observe that a rotated flower is the same as the original flower. It's just rotated, right? So you don't want to be saying learning separate models, one for the original flower, one for a rotated flower. It doesn't make sense. What you want to say is that there is a common flower. Here's what it looks like under different transformations, under different rotations, under different scalings, right? And so what you would do, so this is your standard shift invariant filter operation. You've taken a bit of you've looked at the input, and to compute the output at any location, you're shifting the filter to that position and doing a tensor and a product, right? Now, from the basic pattern, I can create many clones of this pattern and transform each of these clones. So I can start off with a flower and say, let me create a flower rotated at 10 degrees. Let me create a flower rotated at 20 degrees. Let me create a flower that's scaled up by a factor of 1.2, or not a flower, but the filter in general, right? So the filter is now going to be transformed into many different variants, capturing all the transforms that you want the model to be invariant to. And then when you compute the computation, right, each of these guys, transformed variance, is going to be treated as a different filter, and then you'd compute all of these planes, right? So then when you so more generally, basically, each filter produces a set of transformed and shifted maps, right? Each filter is going to give you a bunch of transformed filters, each of which is going to produce its own map. So you're going to stack those things up. And the network itself is going to become invariant to all of the transforms that you have considered. But then this, of course, is going to mess up when you're computing the backpropagation, right? When you're computing the derivative with respect to the filter, you have to keep in mind that this filter produced all of these filters, which produced all of these maps, right? So this is the regular CNN. This is the transform invariance. You're just scanning over all of the transforms, computing the transform filter and scanning with the transform filter. The derivatives have to go back to this filter through all of the transformed variants. So you're going to be computing the derivatives for each of the transformed filters, then untransform it, because after transforming it, you expect to have a one-to-one correspondence, right? So, or some kind of correspondence between the original filter and the transformed version. So if you have the correspondence, you can say this derivative corresponds to this location in the original filter, and you can add things back up. The arithmetic becomes a little more tedious, but that's how it would work. Yes, Sanjay.
So what's the difference between doing this or just, I guess, rotating the image and do all these different rotations and then putting it through?
You could do that too, right? Rotating and scaling. They're strictly analogous. Strictly analogous, right? Except that when you rotate, you're providing greater variety to the input. So when you're rotating the input and trying to train the network, you effectively end up having to learn filters for every transform. You're not keeping track of the fact that the same filter, that the different patterns you see are transforms of the same basic pattern. But otherwise it's analogous. So CNNs are shift invariant neural networks for shift invariant pattern detection. They are equivalent to scanning with shared parameter MLPs. The parameters can be learned through regular backprop, like a regular MLP. Also, like a regular MLP, individual layers may either increase or decrease the span of the representation learned. And the models can be easily modified to include invariance to other transforms, to not just shift invariance, but rotation invariance, rotation and shift invariance, scale invariance, scale and shift invariance, all combinations, right? Now, what about the exact location? So far we've said, I want to find out if there is a flower, but then I want to add this extra bit. I want to say, where is the flower? We haven't actually dealt with this, right? Now, we could implicitly deal with this by saying that, when I do the max in the final layer, I'll see which one gave me the max, and that's actually going to give me some indication of the location of the flower. Or you can do something explicit, which is the more popular thing models like YOLO. So what you do is, this final layer now actually produces two outputs. One is the standard class output. The second is an output which gives you the coordinates of the bounding box of the object that you're looking for from the final representation layer. And now when you train your model, you can also use the same thing to predict the joints of a stick model if you're trying to do pose detection. If you walk past the passage from Hillman to Newell-Simon, Gates to Newell-Simon, you've seen these figures. This is basically what you'll be doing, right? Trained really well, of course. Now, how exactly would you be training this model? So if you want to train the model, you want to compute two divergences. One is the cross entropy loss over here. The second is typically going to be either an L2 loss or some variant of it. And the actual divergence that you'd be minimizing is some weighted sum of the two, which assigns importance to both finding the pattern and finding the location of the pattern as you deem fit. And that is what is going to be backpropagated. Nothing really changes. Other variations, you can have very deep networks, 100 or more layers in an MLP. This is a formalism that we've called the ResNet. You're all familiar with this by now, right? Something that you will actually deal with is depth-wise convolutions. Depth-wise convolutions, going to turn up in homework too. Instead of multiple independent filters with independent parameters, use a common layer-wise weights and combine the layers differently for each filter. This was the MobileNet. And if you haven't actually worked with MobileNet yet, you should be working with MobileNet for your homework too, right? So this is what the model is. Now look at your conventional convolution operation. So here is this stack of maps for the Lth layer, output of the Lth layer, and your filter is going to look like this, right? Your filter is a cube with many small planes. And what you would do is you would be placing the filter on this guy. Now, the way I explained it, I said you place it, you compute a pointwise product and sum the lot. But there's a different way of thinking about it, that you only perform a local convolution in each map. So this plane over here, this outermost plane is going to be scanning with this outermost plane over here. The second plane in this filter is going to be scanning the second plane. And so you can have a layer-wise convolution over all the maps and then add them up. And the result is the same. Whether you add initially or add afterwards, it doesn't really change. Change matters. And in fact, when you do your actual operations using PyTorch or TensorFlow, this is probably going to be a little more efficient than collapsing things up front, right? So now when you have many filters, what do? You have one such filter you have one such set of weights for each filter, right? And each of those is going to be scanning the input. Each of those is going to be producing many layers of planes, and then they're going to be summing all of them, and you're going to get one map per filter. That's the convolution operation, right? So in depth-wise convolution, instead of having all of these guys be independent and then performing the collapsing, you change the order of things. You have one filter is basically one set of planes scanning the input and producing several planes. And then for these outputs, the only thing that differs is the weights with which these planes are combined. So in your standard convolution, all of them are given a weight of 1 when you combine them, right? Here you're going to say that I have created one set of planes, and this first one is maybe obtained by doing 0.1, 0.2, 0.3, 0.4, 0.5. and the second one is contained by maybe doing 0.2, 0.2, 0.2, 0.2, 0.2. So you're going to be collapsing them with different weights, and you still get different numbers of planes. This is just a different way of sharing parameters. But then if you compare what standard convolution and depthwise convolution do, this one tends to be far more efficient in terms of parameters, and as a result far more effective. So here, for example, if I have m input channels and n output channels, so I have n filters, and if the span of the filter is k cross k, then each filter requires m cross k parameters, right? And I have n of them, so I have n times m times k squared parameters and all. Here the initial scan is done only once, so I'm going to need just m times k squared parameters to construct this structure. And then subsequently for each of the output planes, all I need is one set of weights, which is going to be whatever this is, m weights for each of the n planes. So you have n times m parameters. So if you compare these two, you can see that this factor of n in the nmk squared goes away, and the total number of parameters can be an order of magnitude smaller, giving you a much more efficient use of parameters and actually a much better models as a result. So the story so far, just adding to the everything that we've seen. So we can also make predictions related to the position and arrangement of target objects, and you have variations which exist to give you greater parameter efficiency in the model, right? Now this last bit, give me a minute and then I'll stop. What do the filters actually learn? These are what we call the receptive fields. So the patterns in the input that each neuron sees is the receptive field. Now for the neurons in the first layer, it's very obvious. You can just look at the weights and you know what patterns it finds. But in the neurons in the subsequent layers, to find out what pattern it fired in response to, that actually has to be computed and is typically specific to the input. Different inputs will make the neurons in subsequent layers fire for different patterns, right? So here are some examples of from ImageNet that I should have cited the paper. So this is a classifier that has been trained to detect all kinds of classes. When it's given examples of faces, here are the lowest layer neurons, receptive fields, and you'll observe that the lowest layer neurons are the same regardless of the kind of patterns that it's looking for, right? But then when you go to the next layer, you find that when it's looking for faces, the next layer begins looking for things like eyes, noses, and such like. For faces, for cars, it begins looking for things that look like patterns of car, components of cars. For elephants, it finds little bits of elephants. For chairs, it finds little bits of chairs. And then as you go up further, later layers actually begin looking like, for when you present them with faces, they begin looking, firing in response to face-like structures. For cars, you have neurons firing in response to car-like patterns and so on. So actually the kinds of patterns they end up searching for become more complicated and more varied as you go from the bottom to the top. You have all kinds of training issues, the usual stuff. So standard convergence issues, the number of parameters can quickly blow up. I leave all of these for you to check up on the slides. We'll actually close, we have a little bit of the history of ImageNet on the slides. Take a look. It's very interesting how once CNNs came into the picture, the performance on detecting, classifying images went from having something like a 50% accuracy error rate to having a 3% error rate over just a couple of years. And that's because these models are so very powerful, right? And of course, you're going to discover this in your homework. Questions? Thank you.